lunch, I'll leave my room open. Just kind of knock on the door if it's not open. Or if you have access to a computer in another class, you can work on that. That's fine. I need the web quest in the box by the end of the day. Okay, so like 2:30. But we're going to use some of the web quest information today as we talk about equilibrium a little bit more in depth, and we're going to do some example problems with that. I'm going to do kind of maybe some general examples for each type of question, and then you'll have a chance to kind of work in your peer groups on some. Then we're going to talk about Le Chatelier's principle. Le Chatelier's was the one with the shifting and the stresses. Remember that from yesterday on the web quest? So you'll use that as reference throughout the day, and then as we go forward, you guys will let me know how many more examples you actually need. So on the reaction coordinate, how does your reaction graph look for an exothermic reaction? So does it go up or does it go down? It goes down afterwards, right? Because you have to make sure you're releasing energy. So I gave you specific quantities to note. So I'm just going to kind of just do a quick sketch. Okay, so what is going to have to be the difference between this part of the graph and then this part of the graph? Why 95? That's the activation energy. It's the energy it takes. Oops, my graph's a little off. The energy it takes to get the reactant energy up to the activated complex, which is the energy peak, and that's 95 kilojoules. Okay? And then what would be the difference between, might not be to scale, what's the difference between the reactants and the product's final energy? Say again? 25. Why? What's that? What did I call, or what's another name for the fact that this is releasing 25 kilojoules of energy? There's another way to say that. So it's releasing heat. What's another way to say it? Enthalpy. So the enthalpy of reaction is negative 25. Or it could be heat of reaction or delta H. Like I said, there's like 5 ways to say some of these things. So from here to here, that difference is about about right there, it seems. That's our delta H of negative 25 kilojoules. And so then I could actually assign values on the y-axis if I wanted to, but I just do it as an example there. Okay, so the role of a catalyst is to speed up the reaction. How though? Kim, how does a catalyst speed up a reaction? Good, so it does it by lowering it in that case because it's going to take a long time to meet the activation energy is very high. So the way you denote this is as a dashed line, and you draw the same exact reaction coordinate, but you're going to draw it with a lower hump in the middle, lower activation energy, and then you're going to go down to further your products from your original reactant. So the reactants and products stay in exactly the same place, but the activation energy changes. So what would be a good activation energy that I could assign for that green graph right there? Approximately. Just shout out a number. I heard 60. Okay. So anything lower than 95 is what I was looking for, because as long as it's lower in activation energy, you're in good shape. Okay, so that's a quick review of catalysts. Now, on your web quest, you did realize that there were these Ks, right? These Ks, which are the equilibrium constants, and they had special rules on how you could write them. But really, it's talking about a particular reaction. That reaction is at equilibrium. What does equilibrium even mean? Who's got me here? Miles? Right, okay, so equilibrium is when we say reactions rates. So what reaction rates? I know what you're saying. So you're talking about the interplay between the reactants forming products. So the way you, and this is just a generic format, but reactants equilibriate when you draw double-headed arrows like that. We call that equilibriates, or it's a reversible reaction. Reactants equilibriate to products. So I call the forward direction. What arrow? Yeah. Okay, so that's the forward direction or the forward reaction. And that's our normal reaction. We go from reactants to products. You're like, oh, we've done this for, I don't know, the whole year so far. But then the reverse direction or the reverse reaction is going from products to reactants, meaning the reverse is occurring. So what he's saying is that the rate of both of those occurring is exactly the same. So the equilibrium is when the rate of the forward equals the rate of the reverse. And that's likely just the generic definition. But you should be able to tell from a graph if the equilibrium has occurred or if the reaction is at equilibrium. So let me show you a graphical analysis of that first, and we'll kind of go back into what the K values are. So I'm going to do a lot of this just freehand, okay? So write down what you need to. You also can just make notes on your web quest if you want to star certain things and go, oh, this is important because we're talking about it again in class. That's why I thought that would be a nice template for you to use as to add notes to. So we talked about these graphs a little bit yesterday, but we only mentioned like the very, very beginning. So if a reaction's occurring, and let's say I start off with all reactants and 0 products. All reactants and 0 products would have a concentration. Remember the concentration graph with time on the bottom? We had that graph similar to this yesterday. Axes? Yes? No? Okay. So if you start off with 100% reactants, I'm going to start them off up here, reactants, and I'm going to do them in green. And I'll start off with products in red, meaning I have 0 products down here on the concentration axis with 0 concentration. So over time, what's going to happen to the reactant concentration as they react? Why is it going to go down?
Because they're reacting with products.
Right, they're reacting, they're being consumed, they're being used up, they're forcing the formation of products. I can't have both, right? Because as reactants are consumed, products are made. What law is that showing? Right, law of conservation of mass or law of conservation of matter, because you can't create and destroy, you have to rearrange. So what happens is the reactants are going to go down over time. Maybe they start to level out. Well, as those reactants go down, you guys are saying the products are being made, so I'm just going to do a generic graph here. Products are being made at the same rate the reactants are going down. Oops. And then as the reactants level out, the products level out. So yesterday we only spoke of, like, basically this first section here. And we talked about the rate of reactions. And I did a little slope exercise where I was like, hey, we started off with 1 molar reactants, and at time, let's say time 20 minutes or something. At time 20, the reactants now are 0.7 molar. Well, how much changed in 20 minutes? How much? 0.3, right? So we're going from 1 molar to 0.7 molar. So there was a 0.3 molar change in 20 minutes. So what's the rate of change? Rate of change is 0.3, meaning the change in the molarity, over what? 20 minutes. So somebody got a calculator? Phone calculator, what does that do? Unless you're doing it in your head. 0.0. 1.5, okay. So that's molar per minute. Okay, so basically you could look at a graph and you could calculate the rate. But as you can see, the reactants are going down by that much. And if I was really good and my graph was perfect, my products, in this case, if we're a 1-to-1 ratio, would be going up by the same amount. Well, eventually, you can see that we level both of them out. So that at that point, and I'm going to draw this as a separate line, where do you see the flat line occurring? That's going to be the time that equilibrium is starting to be met. So I'm going to say that's about like right there, or so. That's really where it flatlines. So at this point, we are at equilibrium because they are flatlined, meaning there's no overall change in their concentrations. However, it's still changing. It's called dynamic equilibrium. So let's look at an example of dynamic equilibrium. So does everybody have a piece of paper they can sacrifice? Sacrifice to chemistry? Maybe not one you've written on? Not too much, please. If you can tear one in half, please. Cool. Okay, so get your piece of paper and ball it up. Okay, here, captains and pilots. So, you can ball it up. Alright, so I'm going to say this side of the room are reactants. All of you guys. And you guys are products, okay? So, dynamic equilibrium means that even though we say things are constant, things aren't really constant. Okay? So let's say we have equal number of people on this side, and I'm going to do this side. We need to make something happen, but then at the end, make nothing happen. Okay, something has to happen, but overall nothing happens. No net change, though there is change. Does that make sense? Maybe? Okay, so let's say there's 20 pieces of paper on this side, 20 pieces of paper on this side. Make something happen. Throw it to the other side. 1, 2, 3, go. Yeah! Okay, so there was 20, and there was 20. Now something happened, right? So we changed that. We made reactants go to products, products go to reactants. But in the end, there still is 20 and 20 on both sides. So that's kind of what it means by dynamic equilibrium. You don't worry about the paper. Maybe we should have written notes to each other. We could have heard them. Oh, dang. Too late now. Okay. So at this point, we have dynamic equilibrium. So we're going to look at that a little bit more in depth. As you can see on the board, which graph is on top? The reactant graph or the product graph on top in terms of like higher concentration? The products are higher, right? The products I have here in red. So at equilibrium, the products are favored. That's what we say whenever the product graph is higher, meaning it has higher concentration, than the reactant graph. So draw yourself another graph, very similar, but show the reactants being favored, not the products being favored. A lot of graphical analysis here, right? So that's why I want you to draw your graphs. So you're drawing a graph where reactants are favored, not products, using the same logic. Who can raise their hand, maybe tell me what's mainly different here? Darcy? Okay, so you're going to say reactants start. Okay, so reactants start up top, products start down low. Okay, so reactants are going to go, okay, slightly down straight, and then products slightly up and then parallel, so they don't cross. So at equilibrium, where the lines have flat lines, zero slope, no overall change, that's at equilibrium. Who is favored? Reactants, and that's this line right here. The top line is reactants. So reactants are favored is the way we phrase that, and that's to express that we have more of them at equilibrium. We have a higher concentration of them at equilibrium than we do the products. So that's how our graphs can be used to analyze like what's truly present at equilibrium and what's not. But what do you notice at equilibrium? Yeah, go ahead, Chloe. Yes, and then allow them to cross. Yes, and that would still leave reactants on top, products on bottom. So she's saying if you've done start with all products and zero reactants and had a cross occur. Same story. Yep. Good job. Yeah.
Is there a graph where the products and reactants kind of like up there, but instead of being parallel to each other, they like cross onto each other and stay on?
And stay. That's a pretty rare situation, but that's when you would actually have exactly the same amount of reactants and products at equilibrium. Many times you'd have one or the other in excess. But yes, it definitely could happen. So what Nick's saying is, could you do this? Reactants merge, and they have the same concentration of the products at the end. But what do you see at equilibrium? Always there's what? At equilibrium, what do you always see? EJ? Well, not in this one, right? That's one where we have them equal. So true, but what you're saying is that there's two things present. So what's always present at equilibrium? Reactants and products, right? So this is a situation where we actually have an amount left over of reactants and produced of products not 100% reacted. So what we have is a situation like, oops, let me come back to that in a second. Oops, this is some stuff from yesterday. My bad. Let me scooch forward. Maybe. Okay, so we talked about that a little bit. Okay, we talked about that. Oh, so what we have is a situation where old school, what we were doing before today, was we were talking about reactions at 100% went to completion. And so we just said no reactants left, all products made. So in our baby minds, when we weren't well aware of equilibrium, we said that we had 0% of the reactants remaining, 100% of products made. And we never actually said that out loud, but we just assumed that things 100% reacted. And we have these characteristics of things that would give us chemical changes or indicate that a chemical reaction happened. What were some of those chemical reaction indicators? Things that evidenced a chemical change. Go for it. Heat evolved. Okay. Something else? Gas evolution. Keep going, guys. Shout them out. Color change, and that's the weird one, right? I'm gonna say color change that's unexpected, because it could be like dye going into water. That's a physical change, not a chemical change. I got two more. What else could you see happening in a reaction that would go, oh, there's a reaction happening? Good. Precipitation. There's probably one more. Yeah. So combustion can mean a couple of different things. One, it does mean a reaction with oxygen, right? We kind of know that. But usually during a combustion reaction, we have heat evolved, gas evolution, and what else could you see? Light. You see fire, right? So you see the light coming from the fire. So I'll say light or fire, and that's going to be kind of the combination of that. That's pretty good, guys. Okay, so you have a good indication of what we actually knew beforehand. When we would see a chemical reaction, we knew 100% completed, but you never knew if there were reactants left over. So let's see if we got all those. Oh, the only one we didn't talk about was the neutralization process, where you form a pure substance like liquid water. So forming pure liquid water, H2OL, with a liquid like that, water is always pure liquid, right? I mean, it could be gaseous, it could be steam, but that's going to be another indicator that a chemical reaction occurred, because if it makes something that's a pure substance, this pure substance, pure liquid in this case, doesn't break down, it doesn't ionize or anything like that, so we say it's another condition where we form a product that would be indicative of a true reaction. And so that's going to be our neutralization process, acid plus base with salt and water. So that's kind of our background knowledge. We kind of know that already. And then what you see now is we actually have these reactions that go to dynamic equilibrium, and you'll see the difference here is that I draw a double-headed arrow, which can be written like that. In the first case, what did my arrow look like to indicate just forward? How did my arrow always look beforehand? Just one arrow forward, right? We never had the reverse one also indicated. So some characteristics that you should know are there's reactants and products left. So that's what you're seeing in the graphs. They're both present at equilibrium, so we can know that now. There's no net change, meaning if one reaction happens, the other one happens too, so there's no net change overall. And there's a rare case where the product's concentration equals the reactant concentration. That's what Nick's graph was saying, where they converge, they merge together. But that's usually not the case. Usually, like EJ said, one is always above the other. And so the way you can indicate that as well, it's called the equilibrium position. And you can see that your your arrows will also indicate the equilibrium position favoring one side or the other. So what does this arrow system mean, you think? This first one. Who's favored? Robbie. Products are favored, okay? So products are favored. And this one over here? Reactants are favored. And we saw how that looked on a graph where one was on top of the other. So you can also see they're represented this way. But there's one more way to represent which side of the equilibrium is favored. And the word favored, it sounds like I'm just saying the word favored and you're like, what does this actually mean? It just means that the reaction's really stable. Those products in this case, products being favored, products are really stable. It makes the reaction happy. It's in a really nice energy state. It's not going anywhere. And in this case, in that particular reaction, the reactants are favored. It's really stable. Those reactants are really stable. They're also very favored, so that they're in a good energy state. There's another way to denote this, though, and it's related to the K expression. Who can tell me anything about the K expression or the equilibrium constant? Look through your note. Look through part 1. I think it was part 1. Maybe part 2? I'm about to look. No, part 2 is little shots. Looking at that picture, or your part 2A. What is the equilibrium expression? Go for it, Jillian. Uh-huh.
Bracket C, and then the bracket is C alpha
And okay, so this is a good expression. This is a really generic expression though. So what we have here is this is the expression for a reaction that I'm going to write out as A, little a is the coefficient to the reactant A, plus B equilibrates to C plus D. So for this particular reaction, A plus B yields C plus D. What you do is you take the two products, and you write their concentrations in the numerator. So you just say concentration of products to whatever power that each of the products are. Those coefficients, C and D, become powers, become exponents. Divided by the reactant concentrations, multiplied by each other, of course, like we have here, A times B, raised to their powers, which their powers, their exponents, A and B, are coming from their coefficients of A and B here. So this is a really generic way to show it, but what you're seeing is that it's always concentration of products over concentration of reactants. So I'm going to show you mathematically how this makes sense with the stuff we were talking about earlier that was more qualitative. So our first example will be, actually let's do the one on your paper. The next sheet that you just got, look where it says Chemistry Chapter 18, Worksheet number 1, write the equilibrium expression for the following. What's HF's name? Say again, Rishi. Hydrofluoric acid, good. Okay, so I'm going to go find those here. I put them up here. I didn't put them on the board, so I'm going to have to scooch back here. Okay. So, hydrofluoric acid equilibrates to what? Hydrogen ion and fluoride ion. That's a 1 minus, okay? And these are aqueous, aqueous, and aqueous. That's going to be important for us to note the states of matter, so do note that for yourself. So, K expression is products of reactants. So here are my products. So one more time. You guys talk in your groups. You guys write your own K expression. Let me see if you can do it first. Products over reactants. We multiply. So I see a couple of you already have it there. The first product is H plus. And what's the coefficient for H plus? 1. Okay, so it's a 1 as an exponent. You don't have to write the 1, but it's nice to know that you know it's there. And then F1, or F negative 1, also raised to an exponent. Coefficient is 1, so the exponent is 1. We are multiplying these, okay? So if you put a dot in the middle, that might help you. But two products, both raised to their coefficients, divided by the reactants, which is HF. And since it has a 1 coefficient, we have a 1 exponent here. That's how you write the K expression, or the equilibrium constant expression, taking products divided by reactants. All right, so now for a mathematical relationship with this. What if on my graph or in a problem I was like, hey, I've got, 1 molar H plus, 1 molar fluorine. Okay, so I'll write that down because I don't want to forget what I said. 1 molar of this and 1 molar of this. And I only have 0.2 molar of the hydrofluoric acid left. First of all, can you automatically tell which side is favored at equilibrium? Y products. There's more of them. We have 1 molar, and 0.2 molar. So you can tell that from the numbers. But then what you should be able to think about is how does that work with the K expression as well. So plug those numbers in and solve for K. You might be able to do that in your head. So you're plugging in at equilibrium 1 molar for each of these, divided by 0.2 molar. So what's 1 over 0.2? 5. K equilibrium expression is equal to 5. Okay, so here's the story. If your K value is greater than 1, products are favored. So write that down for yourself as well. I'm taking a lot of just streamlined notes, and you may have seen this a little bit in your web quest, but this is a quick reminder. K greater than 1 means products are favored. So what does that mean about K less than 1 likely? K less than 1, reactants are favored. Good. All right, now how does that make sense in our mathematical expression, in our little fraction we have here? K expression is what over what? Products over reactants, right? So if I have a K value greater than 1, which part of my fraction is bigger? Numerator or denominator, if K is greater than 1? What makes the fraction greater than 1? Numerator larger or denominator? Numerator. So if products are favored, that makes sense. You have more on the top and less on the bottom, and that's how you have something greater than 1, because the products are favored, the reactants are not. The number of the products is a larger number. How do you have something less than 1? How does your fraction look? Less on the top and more on the bottom, and you have that less than 1, because that denominator, when you divide by something that's a large number, it pulls the number down, so it makes it smaller than 1. So mathematically, it should make sense in terms of your fractions. How you feeling about that right now, guys? So, like, give me 1 out of 10. Like, how much of this made sense? 10's like pretty good sense. 1's like, I'm still not sure what K is. Okay, that's not bad. Do me a favor. Go ahead and do number 2. B. B, which is the second K expression. So, who wants to tell me that? Let me compare with the person next to you before you tell me. What do you think, Leo? Sorry, I'm almost ready for you. Say again?
H2O on top.
Let me pause for a second. Can you tell me, in your reading and looking through the websites and stuff last night, did you guys see anything about what K could not put in it? Exclusions to the K constants? Say again? Okay, so yeah, that's true. You don't put the coefficient inside the brackets. You're going to use this as an exponent. That's an important point. So I'm going to erase this 2 for now. See anything about pure solid? Oh, go ahead. Yes, pure solid, so it'll have an S on it in our reaction. And what would the liquid have on it? An L. Okay, so we see this L here, right? It's probably a little difficult to see in your paper, so that's my bad. It's an L right there on the end. That L means in your expression, you cannot include it. And I'll tell you why in a second. These are gaseous, right? Yeah, those are gas and gas. Okay. So the reason why is because equilibrium is all based on concentration changes. Concentration is molarity. What are molarity units? Moles of solute over liters of solution, right? So if I have a solid, I don't really have a solution, right? Like, I can't change. I'm a pure solid, right? It's not saying I'm in solution. So if I'm pure solid and I don't have a liquid around me, I can't change my concentration because I'm just like what I am. I'm a certain number of moles, or I'm a certain number of grams, not within any solution. Therefore, we don't change its concentration. We don't include it in our K expression. Pure liquids, are they a solution of anything? Is it liquid dissolved in liquid, or is it just pure liquid? Pure liquid, so I don't have a concentration necessarily of that either, so therefore its concentration cannot change. So I'm not going to include this in my K expression. I'll put a 1 as its placeholder. So you'll say K is equal to, I can't put that in there, right? Can't do it. So I'll put 1 in there just as a placeholder, divided by this information over here. How do I write this? Lael, you can finish it up for me.
H2 and then 2 exponent.
So squared, okay, great, times
O2
oxygen's concentration.
and then 2.
Is there a 2 there? Not on that one, there's a 1, right? Okay, good. So that's our K expression for this particular reaction. I think we need to do a couple more of these, okay? So look, and this is not on your paper, so you're going to have to work it from the board here. So go ahead and do these. Write down your K expressions, your equilibrium constant expressions for those 2 reactions. I'm gonna have to break down the stiff matter here. These are not in your paper, no. All right, Kyle, what are you writing for this top one? So concentration of NO
And then the 2.
squared, okay?
Then underneath, you're going to put in the brackets 10-2
Mm-hmm.
with the 1 on top.
Okay.
And then 10-2 with the 1 on top as well.
Beautiful. Okay, so we took our coefficients, we made them exponents, they were all gaseous, so they were fine to go in there. And those brackets mean concentration again. What concentration do we usually express things in? Molarity, right? So we're good to go. All right, so what's different about the bottom one down here, guys? What was weird? Solid, we exclude it from equilibrium expression. It's still there, but we're going to say 1 over, everybody else help me out here. Okay, NH3 concentration times, good, HCl concentration. Beautiful, and those are both to the first power there. All right, so I'm going to do one more of these just to make sure we're fine because it's a little bit more complex, and I'll tell you it's on the next slide, so wait for it. Let me tell you which one. 4 and 5. These are not. Nope, these are handwritten ones here. So if you can't read some of them, please let me know. 4 and 5. Cameron, you gonna help me out with number 4?
I did 1.
Where are you getting your 1 from?
Sorry,
Go for it.
the Mg2.
Okay, so magnesium ion in brackets. Okay,
And then the
bromine.
and then with the 2 exponent.
Great, because there was a 2 coefficient. Over 1, beautiful. Okay, so that solid on the bromine, magnesium bromide side is not going to allow us to put anything in the denominator. You can put a 1 there, you don't have to because over 1 is, the same. So that is our K, and this is actually called a KSP. I'll show you a description of each of the Ks in just a second to show you the thematic way you can express them. We'll get back to that in a second. So, Cinco, everybody. 1. Okay, so what you should see is there's a solid, and a liquid. You can't put Jack in it, right? You can't put anything in it. Yeah.
What's favored in that situation?
So this is K is equal to 1, right? So it's 1 over 1. So they're going to be equally favored, and that's where the graph converges. The graph where we have reactants going down, products going up, and they would converge there because they actually have equal favorability. Good question. All right, so I think you feel a bit better with those. Before I move on to more information, go ahead and do questions 2 and 3 on the paper right in front of you. We'll work with someone next to you, but they give you some indication. Actually, I lied. Just do 2 for now. I'll do 3 with you. Just do 2. It gives you indication of what's present at equilibrium. You probably will need a calculator, so if you don't have one, raise your hand. They're around in the basket. So too. Is there something in your basket right there? Good question. sure it's going to take you a second to plug in your calculator. Who's got me so far? Yeah, Nick?
I was asking if one was solid, you just put one into improve the molarity there with just keep one.
No, you keep one. Yeah, because it would not have a concentration to indicate. Now, give me a thumbs up if you set your K expression up as HI squared over H2 times I2. Thumbs up. And you plugged in your values. And I would definitely put double parentheses or just do the denominator and then divide it or divide the numerator, because it's going to mess up your calculator if you don't have it 100% distinct in your calculator or your calculation. Who can give me an answer here? Chloe, what you got?
401.
401.
5.4.
Should I double check? Who has some consensus here? Say again, Louise. 5.42. Who else got that? I'm just gonna double check you guys. I got 2 different answers. I do believe you and stuff. Go ahead and set up the K expression on number 3. You're waiting on me. I have this in my notebook, but my notebook's away. You do have to double up on some parentheses just to make sure. And the answer is 5.41 or 5.42, I guess. Yeah, we're good here. Okay, so what does that tell you? Who is favored? Products are favored. What was your graph look like? What would your equilibrium graph look like? Who would be on top? So products would be on top, reactants on bottom. Good. All right, so that's feeling pretty good. Let's look at a couple more in terms of how do you anticipate a reaction to equilibrium, not given anything about its concentrations at equilibrium. So, yes, ma'am. Yeah, you do have to make sure that you're very specific in where you put your parentheses. The way I did it in mine, because I do it all in one step versus in 2 separate steps, I put it in here as it parentheses, blah, 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 -2 squared, and then in parentheses to keep all of that in the numerator. And then I double up on parentheses down low to keep all the denominator together so that it distinctly divides. Because if you don't, it's going to multiply by this at the end and your answer's way skewed.
Right.
Okay, so just learn how to use your calculator. And on the exam, sorry, but you guys get the scientific calculator's a little blue one, or something similar to that. You can't use your own because they may or may not. They likely won't allow you, and then they have specific examples of which you definitely can't use, like the special ones with solvers and stuff. So, okay, let's go to here. This is on your paper. Oops. This is on your paper on the, let's see here, upper right-hand side, where it says number 1, calculations involving equilibrium. I'm going to give you guys a couple minutes just in groups right now to do questions 1, 2, and 3. So I think you're capable of doing those, but you gotta let me know if you need some help. You gotta go help solve the board, or we'll give you a chance to go jump in first. So on the right hand side, questions 1, 2, and 3. I should hear you talking in groups if you need to. And if we get all this done in class, you won't have to do any of this at home. You just have ABC book stuff. That's my goal. Take about 1 more minute. Alright, I'm going to start back up at number 1 real fast. I think that you're probably just very good at setting the K expressions, just making sure you're solving it correctly in your calculator. Thumbs up if you got this K expression with PCl3 times chlorine over PCl5. Ooh, let's practice naming those. What's PCl3's name? Loud and proud, you got this. First, I guess you should identify first, is it ionic or covalent? It's definitely covalent, it's got 2 nonmetals in it, okay? So when you name covalents, how do you say the numbers of them? Phosphorus trichloride, so use prefixes, good. So phosphorus trichloride, this is chlorine gas, and then phosphorus, what's 5? Penta, good, so 5 is pentachloride. All right, so when you plug your values in, what do you guys get for your K value? Shout it out. Point what? 0.4? 0.4. Okay, regardless, it's small, right? So K is less than 1, who's favored? Reactants are favored. Okay, great. I'm trusting you guys all those values. My values are hidden away in a book. All right, on your next one, you should have set up C squared over A squared times B, plugging your values in, squaring your numerator and one of the denominator values, appropriate parentheses. Who's confident they put that in the calculator correctly? Rishi. Can I get a thumbs up? 7. Yeah. Thumbs up. No, I hear some questions. Where's my book at? I believe you. I totally believe you guys. I like to pretend you're good. It's your math. I could just recalculate them all, but it might be easier if I just pull this out. I got. This is not the right one. Hold on. Well, you know, super fast at finding this, guys. Who has another alternative? 15 what? I think that's right. Wait. Guys, let me just recalculate for you. Just let me recalculate for you. You're putting a negative, not a minus, squaring it, divided by 5.50. I trust that you guys can plug it in your calculator, but you never know. Make sure, and is your setup exactly the same?
Yeah.
I'm just going to verify. My answers are hidden away in my notebook. 1,528.6. How do you put in your calculator? If you are not confident with doing it all at once, just do it separately. No one needs you to do it all at once. Plug in, just do that squared equals, then divided by whatever this value is through multiplication. Yeah. If you're gonna go ahead and immediately divide without calculating, like equaling in your calculator, then yes. Because what's gonna happen is your calculator's gonna think you're doing this squared, and it's gonna go, oh, let's divide by this squared, and then at the end we're gonna multiply by this final thing. But that's not true. You have to do PEMDAS, right? So top, separate from the bottom, and then divide, whatever you gotta do to make it work, but this is the true answer. I can help you on your individual calculators at that point in time. How in the world do you solve this final one? So using your generic setup, you got your setup. Give me thumbs up on this one. methanol, and so forth, squared H2. When you plug in information here and it says solve for the H2 in the vessel, which is X over here, as I've denoted, how do you rearrange this formula to solve for X? Lindsay? Okay, so you multiply the bottoms on both sides. Okay, so X squared times 1.402, and this is X squared times 1.402. So these cancel over here. So she's saying this times 1, so what's 1.609 times 1.402? Can you do that for me? Anybody? 2.26? And that's still X squared because it's not been negated. That's equal to what was left over here, 0.818. So then how do you further simplify? Divide by 2.26 on both sides. Okay, so that cancels. X squared is equal to what's 0.818 divided by that? 0.323. Okay, like that. Okay, so then how do you solve for X? Square root. All right, so we're good with that. What's that final answer? Say again? 0.602 molar. So that should be your final. But that's just making sure you can get from your X in the denominator back to the top and the rearrange. So this is not a math heavy area, but it does take some thought to actually rearrange your formulas. Okay, so let me pause for a second. At this point, you've done everything at equilibrium. We've just said, these are the concentrations at equilibrium. This is the equilibrium constant expression. We plug values in, and we just go with the flow. We calculate K ourselves. What if I start you off at an area that's not at equilibrium, but it's before equilibrium? We actually have to get ourselves to equilibrium before we can plug values in. So that's what we're going to do next. In about 10 minutes or so, Justin's going to do a demonstration for us, but not yet. So Justin, go do what you got to do, man. We're going to be a little bit longer. So let me go back to, I don't know if it's on this next slide or not. Nope, sorry. Let me go back to number 3, which was on your worksheet that you had in front of you. I'm just going to write it down though, okay? So look back at number 3, which is your number 3 on the left-hand side under worksheet 1. It said given 2A, and you might want to write this on a separate sheet of paper if you don't have enough space right there. So 2A gas plus 2B gas equilibrates to C gas plus 4B solid. First off, you had to write the equilibrium expression. Can you go ahead and tell me what the equilibrium expression is? K is equal to what? C over A squared times B squared. All right, so that's our equilibrium expression, and we can only plug in equilibrium concentrations there. You can never plug anything else into that equilibrium expression because it's at equilibrium. So this is an equilibrium reaction, and then it says the initial concentration of A was 4.0 molar and B was 4.0 molar. What would be the constant, meaning the equilibrium constant, if at equilibrium 2.0 molar of A had reacted? So it's saying so much reacted. So you have to figure out from the initial how much changed to what's left at the end, and that's called an ice box. Remember, we briefly mentioned this probably a week before break. An ice box. Set up an ice box with this, and I'll tell you what each of these values mean. So I is initial. So I means initial. So initial concentrations go plugged in there. C means change. So we're talking about what actually occurred during the reaction. And then E means, can you take a stab at that? Equilibrium. Right, so we're going to actually, at the end, if we have equilibrium values, these can be plugged in to K, and that's what we would then use to calculate K expression. So, at initial, what did it say, 4.0? 4.0 molar of A existed, and 4.0 molar of B existed. So we're plugging those in there under the A and B, under the alongside the I. And I said, what would be the constant if at equilibrium 2 molar of A reacted? So if 2 molar of A reacted, how much change occurred? How much reacted of A? 2 molar. So I'm subtracting, because it reacted, meaning it is consumed. 1 second, Robbie. We're subtracting 2 molar of A. This is like an addition and subtraction box here. Robbie, question?
Yeah. To find the
Yes, you would. And I'm going to show you how to quickly do that in your head. Because it is a reaction, right? So we would have to look at mole ratios, which is why we have the coefficients already here denoted. So if 2 molar of A reacted, do you see that A and B are in the same ratio? A 2 to 2 ratio? So if 2 moles of A reacted, how many moles of B would also react? 2, because it's in the same ratio. So we're also going to subtract 2 from the B because they are a 2 to 2 ratio. However, as reactants are consumed and used up, what are they going to make? They're making products, right? So they're making C and D, but nobody cares about D because guess what? It's not in our equilibrium, so I'm just going to scratch through the D section because I don't really need to know that part. So if 2 molar reacted from A and B, but you'll notice the coefficient of C is 1, how much do you think would be made, produced of C? Half of that, right? So what's half of that? 1 molar. So we're adding, because we're producing on the product side, 1 molar of this. So the way I'm thinking most of you guys are thinking about that is if 2 molar was consumed, and this exists in a 1 to 2 ratio, basically what I think people are doing in their head is 2 molar or moles are consumed, and then I would make C in a 1 mole of C versus a 2, I'll just do A, 2 mole of A ratio. That's basically multiplying by half or dividing by 2, and most of you guys are saying that's down 1. And that's because of the ratios up here. So that produces 1 molar. Yes, ma'am?
When you divide by 4, what are you doing with the negative 2?
I'm actually going to subtract that now. Yeah, I'm almost done with that part. So before I had initially 4 molar, and it didn't say I had any products. I'm just going to assume I had 0 products here and here, 0 molar. The changes that occurred were minusing from A and B, 2 molar each. So how much is at equilibrium? 4 minus 2 is 2 molar at equilibrium, and that's because we knew 2 molar had reacted. This is 4 minus 2, so that's 2 molar at equilibrium. We converted that in our head as a mole ratio. We've said 1 molar of C was produced, so what's this? 1 molar. Nobody cares about D because it's not in our equilibrium. So now we can plug these values in to our K expression. Let's go ahead and do that. So, yeah.
How did you get this 1 more?
We looked at the ratio between the reactants and the product, that product of C. We said if 2 molar of B reacted, and we see that this is a 2 to 1 ratio, half of the amount of C is produced. So if B used up 2, C is made at half the rate, so it makes 1. And so, let's plug this into K. What goes in the numerator of K? What value? 1, okay, over 2 squared for A times 2 squared for B. So, what's 2 squared times 2 squared? 16. So 4 times 4 is 16. So what's 1/16? 0.0625. Good. So K is less than 1. Who's favored? Reactants. Good. That's an interesting one because that's going to take us to some time to get from I initial to E equilibrium. We'll do another one like that shortly. Okay. Let me take a break. Pause for me. I have about 25 minutes left, and that's going to be for Le Chatelier's principle. I'm going to give you guys a break from me. Let's watch a quick video on Le Chatelier's principle. Okay. So if you just keep your eyes open for me, you don't have to write anything down. I'll go to YouTube for this.
What would you say is the most important discovery made in the past few centuries? Is it the computer, the car, electricity, or maybe the discovery of the atom? I would argue that it is this chemical reaction. A nitrogen gas molecule plus 3 hydrogen gas molecules gets you 2 ammonia gas molecules. This is the Haber process of binding nitrogen molecules in the air to hydrogen molecules, or turning air into fertilizer. Without this reaction, farmers would be capable of producing enough food for only 4 billion people. Our current population is just over 7 billion people. So without the Haber process, over 3 billion people would be without food. You see, nitrogen, in the form of nitrate, NO3, is an essential nutrient for plants to survive. As crops grow, they consume the nitrogen, removing it from the soil. the nitrogen can be replenished through long natural fertilization processes like decaying animals. But humans want to grow food much faster than that. Now, here's the frustrating part. 78% of the air is composed of nitrogen. But crops can't just take nitrogen from the air because it contains very strong triple bonds, which crops cannot break. What Haber did, basically, was figure out a way to take this nitrogen in the air and put it into the ground. In 1908, the German chemist Fritz Haber developed a chemical method for utilizing the vast supply of nitrogen in the air. Haber found a method which took the nitrogen in the air and bonded it to hydrogen to form ammonia. Ammonia can then be injected into the soil, where it is quickly converted into nitrate. But if Haber's process was going to be used to feed the world, he would need to find a way to create a lot of this ammonia quickly and easily. In order to understand how Haber accomplished this feat, we need to know something about chemical equilibrium. Chemical equilibrium can be achieved when you have a reaction in a closed container. For example, let's say you put hydrogen and nitrogen into a closed container and allow them to react. In the beginning of the experiment, we have a lot of nitrogen and hydrogen, so the formation of ammonia proceeds at a high speed. But as the hydrogen and nitrogen react and get used up, the reaction slows down because there is less nitrogen and hydrogen in the container. Eventually, the ammonia molecules reach a point where they start to decompose back into the nitrogen and hydrogen. After a while, the two reactions, creating and breaking down ammonia, will reach the same speed. When these speeds are equal, we say the reaction has reached equilibrium. This might sound good, but it's not when what you want is to just create a ton of ammonia. Haber doesn't want the ammonia to break down at all, but if you simply leave the reaction in a closed container, that's what will happen. Here's where Henri Le Chatelier, a French chemist, can help. What he found was that if you take a system in equilibrium and you add something to it, like say nitrogen, the system will work to get back to equilibrium again. Le Chatelier also found that if you increase the amount of pressure on a system, the system tries to work to return to the pressure it had. It's like being in a crowded room. The more molecules there are, the more pressure there is. If we look back at our equation, we see that on the left-hand side, there are 4 molecules on the left and just 2 on the right. So if we want the room to be less crowded and therefore have less pressure, the system will start combining nitrogen and hydrogen to make the more compact ammonia molecules. Haber realized that in order to make large amounts of ammonia, he would have to create a machine that would continually add nitrogen and hydrogen, while also increasing the pressure on the equilibrium system, which is exactly what he did. Today, ammonia is one of the most produced chemical compounds in the world. Roughly 131 million metric tons are produced a year, which is about 290 billion pounds of ammonia. That's about the mass of 30 million African elephants, weighing roughly 10,000 pounds each. 80% of this ammonia is used in fertilizer production, while the rest is used in industrial and household cleaners, and to produce other nitrogen compounds, such as nitric acid. Recent studies have found that half of the nitrogen from these fertilizers is not assimilated by plants. Consequently, the nitrogen is found as a volatile chemical compound in the Earth's water supplies and atmosphere, severely damaging our environment. Of course, Haber did not foresee this problem when he introduced his invention. Following his pioneering vision, scientists today are looking for a new Haber process of the 21st century, which will reach the same level of aid without the dangerous consequences.
All right, so you saw the part where he said at equilibrium, and then he said it stresses it out. So what were some What were some of the stresses that you saw in your reading last night in your web quest? We did a couple of these. Sorry, I'm scooching through. These are problems that we're not going to do. What were some stresses that could stress at equilibrium? Go for it, Chloe. Pressure. What else? Darcy. Change in temperature. What else, Emily? So more particles, either more reactants or more products, right? It just depends. One more. Yeah? Okay, so I'm going to include that as an increased number of particles. How can pressure also be changed? You could change pressure by changing the volume of the container. So there are different stresses that can be placed on things at equilibrium. So Le Chatelier's principle, or Le Chatelier's principle. It's just basically we're at a happy place, we're at equilibrium, and the reaction is very stable. At that point, we stress it out by adding some external variant, concentration, temperature, pressure. And I'm going to see if this will work. Justin has a Bunsen burner going. He's going to go ahead and demonstrate this and see if this will work in the next minute. If not, he's going to let it chill for a while. He has, hold up to me, has a kind of a pinkish solution that's cobalt 2 fluoride, and it's at equilibrium with itself through cobalt 2 and fluoride ion. He's going to go ahead and put one in the ice bath. He's going to set it in there, and we're going to see if this process it changes an endothermic change or an exothermic change. So we're going to see that maybe change color over the course of the next couple minutes. He's also going to hold up one and he's going to put in the Bunsen burner plane for a little while. So he's just going to hold it at an angle above the plane. And let's see if it changes color in the next minute or so. Hold it up some more. You guys see it changing color at all? So I'm going to hold a piece of white paper behind it. It's a little higher for me. So cobalt, and do you guys even know what cobalt looks like? I've never heard of like cobalt metal, like in a ring or something. So, hold on. Sorry, I gotta do the color. You guys see the color change? What color occurred? Well, here, we'll have a little higher. So, do you see that color change is like more purple color now? Okay, and so you can see that originally, so put that in the thing of cool, because it's actually turning really fast. So he's going to cut out the Bunsen burner for me. We're going to let that cool down for just a couple minutes. And what we should hope is that at the end, the cobalt that we changed from pink to bluish purple will go back to what it is in the cool situation. So after he's going to let that temperature cool for about a minute, and then we'll pop it back. He's going to let the hot one cool for about a minute, and then he's going to pop it in the ice bath, and we hope that they change the same color. So what he did was, what stress did he add? He added heat, right? So that's going to be relevant to endothermic and exothermic reactions, which we're going to talk about here shortly. So this is just a graphic to show you that things will be happy, you stress it out, and it's going to find a way to reestablish equilibrium or reestablish itself back to equilibrium. The only way it can establish equilibrium again is shift left, shift right, or no shift. When I say shift, I mean increase the forward direction or increase the reverse direction, or neither side would be increased, meaning it would have to resolve its stress another way. So some of the different, these are what you have on your web quest. If you want to add anything to that, your little list already, that would be wonderful. Is it cool down enough? Don't touch it. Give it another minute. I don't want you to break the test tube. So, all right, so change in temperature. Either that's going to be relevant to inter and exothermic reactions. Adding or removing, like I said, taking away particles is removing. Adding is adding increase in concentration. I'll talk about common ion in a second. Increasing the pressure, which in fact is actually more of a change on volume than a change on pressure, or adding an inert gas, which means that a gas that's not reactive. So what are some good examples of inert gases? Non-reactive gases. Shout them out. Anything in the noble gas category, right? Helium, neon, argon, krypton, things like that. Thumbs up if I can move on. These are the different stresses. Okay, this is nice because you guys already have a good, decent background knowledge on it. So this purple here is basically what we just said that Le Chatelier's principle states. If a system's at equilibrium and you stress it out, the equilibrium will respond to relieve the stress by shifting. Okay, so you'll shift left or right, or no shift. So I think if I demonstrate some of these through an example, we'll kind of make sense of this. So this is my first example. This is the Haber process or the Haber process, as the video stated. You'll see that I have some gas making ammonia, and this 92 kilojoules of energy being a product. Does that mean energy is being produced or consumed? It's being produced. Is that energy being produced, is that an exothermic reaction or an endothermic reaction? Exothermic. Okay, so that's exothermic. Delta H is a negative 92 kilojoules of energy. All right, so if I heat the reaction vessel, what we do is we treat heat, as you can see it's exothermic, we treat heat as energy, and we treat it like it's a product, just like any other product, like this product over here. So here's the deal. My system's at equilibrium. I stress it out by heating it up. So basically, I've added energy. That's the stress. I have to find a way to get rid of the stress. I have to find a way to get rid of energy. Which direction, if I reacted it in the forward direction or the reverse direction, would get rid of energy, consume it? What do you guys think? You got two options. Why reverse? Say again? Right, you want to consume the energy. So if you go in the reverse direction, these are consumed, these products are consumed, and these reactants are made because you're reverting back. But if you go in the forward direction, you're going to make the products, which that would make more energy. That would just doubly stress the system out. We don't want to make more energy when we want to consume it. So the stress was added energy. So we are going to shift which way? Shift left to consume that energy and come back to reestablish equilibrium. Good job. All right, so let's go. I'm going to skip the second one for a second. Let's go down here. Remove NH3. Is that a product or a reactant? Okay, so I've removed a product. So that's the stress. Oh no, I don't have enough products now. Which way do I shift to reestablish? I'm going to shift right because what am I doing when I shift right? I make more product, right? I'm going to re-establish the amount of NH3 I need. I need to increase it again. Let me keep doing this example out loud. Have some more. All right, so what if I add excess H2? Where's H2 out of here? It's a reactant. So my stress is I've added a reactant. All right, so, oh no, I've got too many reactants. How do I alleviate that? Why shift right? Well, it's not about the products. It's about eliminating my stress. So if I add a reactant and I shift right, what am I doing to reactants? You're consuming them, and that's what you want to do. You want to narrow in on the stress and fix it. So we've consumed reactants as we go forward. Now here's the pressure and volume ones. Let's go back up to here to pressure. All right, so what causes pressure again? You have a little box of air, right? What's causing pressure? Well, no, let's go really narrow in. The molecules themselves are causing pressure, but what are they doing? Hitting the sides of the walls, right? So pressure is just about collisions with a container wall. So if I've increased pressure, my problem is pressure is increased. So I'm going to say I have too many collisions. Well, those gas particles are what's causing those collisions, right? So how do I decrease the number of collisions? Do I shift to the side where there are, how many moles of gas are over here? 4, so that's 1 plus 3, right? So there's 4 moles of gas over here. Or do I shift to the side where there's only 2 moles of gas? Why 2? Less what? Moles, meaning less molecules, EJ? Yeah, you want to actually, that's a good way to say it too. So we're saying too many collisions are occurring, so we want to shift right because that's going to consume the 4 moles of gas. They're going to go down. We don't want them anymore. We want to lower the number of moles. And it's going to go towards the 2 moles of gas, and that's a lower number. That's going to cause less collisions. That's going to fix our pressure. So that's good. That is a shift right. Question? Yes. So as you go forward, as you go in the forward direction, the law of conservation of energy means you can't create or destroy. You have to just rearrange, right? So as you go forward, you are making products because you're producing products, but you can't produce them from nothing. You have to lose some of these because these get rearranged to form these. So I consume or use up the reactants as I make products. But if I'm going reverse, I'm making these and I'm consuming the products. It just depends on which way you're going here. Right. Who feels like they are maybe a 1 out of 5? I'm sorry, out of 10. How do you feel about the shots right now? Understanding the shifts. I got more than one hand up for most people. Okay, let's do another example like this. You guys have one on your paper. You turn on the back side where it says practice Le Chatelier's principle. First one, it says H2 plus Cl2 yields HCl. How about you guys do that in your groups right now? Go ahead and do one, and then we'll see where we go from here. From the back of the lecture note sheet. So Justin just walking around to show you that the color changes are coming back. You can see they're going back to pink. All right, come back to me. I hear some good conversations, but I actually feel like we're a little confused still. So let me go through one more with you, and then we'll jump in the next one in groups. So we have our reaction. Our stress is what here, guys? Shout it out. What's our stress? Temperature. We have too much energy. Oh no, you're stressed out. So you have too much energy. You have too much of a product. How do I get rid of the product? Shift which way? If you shift right, you're making more product. That's exasperating the problem, right? You don't want more energy. The problem is you got too much energy. You got too much temperature. So how do I get rid of energy? You shift away from it. Good. It's like a seesaw. If you have an equal amount as an equilibrium and you increase the energy, oh no, you need to equal it back out. So you shift back towards the other side. So shift left in this case. Thumbs up if you feel good with that one. Energy ones are a little bit difficult. Okay. Decrease the volume. Now, this is an interesting one because how many, let's kind of go back. If I have my box of air, decrease your volume, what happens to pressure? Okay, so really decreasing volume causes an increase in pressure. That means we have too many collisions. So the stress is I have too many collisions. Which direction would eliminate some of those collisions? So the last time we did this, we had to count some things. So what are we counting here? Moles of gas. And it has to be moles of gas because gases are the only things that freely move around and bounce off container walls. If you have liquids or solids, they don't really move. Don't count them. How many moles of gas do I have over here? 2. How many moles of gas do I have over here? Which side is favored? Neither. So you say no shift. No shift. Okay? Just to make sure we're saying shift there. Okay. So in this case, that was an equal amount of moles. That's why neither side was favored. All right, adding HCl. What am I adding? I'm adding that's a product, right? So if you're adding a product, oh no, I have too many products. Which way do I shift? Shift left to go away from products to consume them and remake reactants. So you're going to shift left to eliminate products. Adding NaCl. Do you see NaCl up there?
No.
Nope. If it's not in equilibrium, it's not going to affect equilibrium. So that was a good one because you might say, oh, but there's a Cl and there's a Cl, but that's a gas and this is not, so it's probably not going to interfere at all. So that's going to be a no shift. Removing Cl. Cl is a what? Or chlorine gas is a what? It's a reactant. So you're removing a reactant. So what's our stress? Well, our stress is I have too few reactants. I want to make more, so if I have too few reactants, my job is to make more reactants. How do I make more reactants? Shifting left by going towards the reactants to make more of them. So really talking to yourself to go, here's exactly narrowing down what the exact stress is and realizing that you can go one way or the other to alleviate that. That's what you're looking for. Let's do one more together. See where we are. I'm going to give you guys a minute to get a head start. Second one up here. What's up, Caroline? If you're able to move on, you can keep on moving on. You'll be finishing the back side of this. right, I have like 2 minutes left here, guys, so I'm gonna work this last one with you here, okay? What did you guys say for A? Shout it out loud and proud. Shift which way?
Right.
Left.
Raise your hand if you say right. You were good, because energy is currently, an endothermic reaction is a reactant. If you increase the temperature, that's increasing the energy. How do you get rid of energy? Do you shift towards it to make more, or shift away from it to consume? Away. So you're shifting away from it, so that's a shift right. Good job. Increasing the volume. What does that do to pressure? Decreases pressure. Okay. Oh no, I have too few collisions. I want to make more collisions happen. How do I make more collisions? This is a 2. So how many moles of gas are over here? That's a number 2. Okay, so there's 1 mole of gas over here. How many moles of gas are over here? 2 moles of gas. My stress is too low pressure, meaning too few collisions. That's my stress. Fix my stress. Shift right, because you want to make more pressure. You want to make more collisions. And that would be 2 moles of gas versus 1. Adding helium. No shift, because there's no information there for helium. It's an inert gas. Adding carbon monoxide. Shift which way? Left, because carbon monoxide is a product. Oh no, too many products. I don't want those products. I shift away from products. I shift left. Heat the reaction vessel. Currently, yes. And do you see that E and A are basically the same thing? Heat, energy, temperature, they're all the same thing here. So that's a shift right again. All right, so here's what I'd like for you to do. The back side of that has 2 more examples that are 3 and 4 for you. And I want you guys to try your best on the questions that say worksheet 3 through the other side. 1, 2, 3, 8, 9, and 14. So basically, you're going to finish the back side of the worksheet with it. And that's it. We'll check those tomorrow to make sure you're fine with those. And you guys got your scantrons back yesterday from your test, yes? I'm going to have you guys come, have a little come to Dunes meeting with me. We're going to go over some of those questions in the test, and make sure you bring that tomorrow so don't lose that scantron. Okay? 1 second. Yeah. You're doing the back side, entire back side. We were just working on? Yeah, the entire back side.
Where's your pen back?
I'll give you guys a copy. I want your homework in the box before the end of the day. So your titration work and your web test. Yeah, if you had an issue with it, I'll be on that. Surprised you got this worksheet? You got the worksheet?